Students, thank you for joining me in this third installment of my Special Topics Lecture 2's systematic review of Chapter 6 through 8 from last semester of General Chemistry. We're going to begin today by covering ionization energy and periodic trends in the periodic table. You might notice that a lot of the footage looks stitched or cobbled together from previous segments of footage that I've had from earlier videos. That happens to be true, so please just ignore it if you see my hairstyle or clothes change. I'm just sort of capitalizing on earlier footage that I've already made so that I don't have to reinvent the wheel. Are you ready then? Let's go ahead and get started. So believe it or not, it takes energy to remove electrons from an atom, even for atoms that want to give up their electrons. The energy required to remove an atom's electron is called its ionization energy. The first ionization energy is the energy required to remove the first electron from a neutral atom. The second ionization energy is the energy required to remove a second electron from an atom. And the larger the ionization energy, the harder it is to remove an electron. Electrons in higher energy orbitals, by the way, are further from the nucleus, so they're easier to remove. For example, it's easier to remove an electron from a 3s orbital than it is from a 2s orbital, because a 3s orbital electron is further away from the protons in the nucleus that are sucking it in than a 2s orbital. This table shows us various ionization energies for different elements. Sodium, for example, you'd imagine, would want to give up its first electron because it wants to be isoelectronic with neon. But it still takes energy to remove that first electron. In fact, it takes 496 kilojoules to remove that single electron from a mole of sodium. At that point, sodium now feels like neon. How much energy does it take to remove a second electron from sodium, making it Na2+? Well, you can see that it takes a lot more energy. And I hope that makes sense. Sodium wants to have a +1 charge, but it does not want to have a +2 charge. For magnesium, we can see the amount of energy it takes to remove its first electron and its second electron. At this point, magnesium now also feels like neon. Is magnesium going to want to give up that third electron and feel like magnesium 3+? Absolutely not. So you can therefore see that there's a dramatic increase in the amount of energy required to remove a third electron from magnesium. This trend holds true for each of the elements in row 3 of the periodic table. You'll also notice as we go down a column that the first ionization energy for each of these elements, which is really going across a row on the periodic table, sodium to magnesium to aluminum and so forth, generally goes up. So as I go from sodium to magnesium, it becomes more difficult to remove an electron. There's an exception with aluminum, but then the trend continues going from silicon to phosphorus and so forth. Why in the world would it be harder to remove a first electron from each of those elements going across a row from left to right on the periodic table? The answer is because as you go from left to right, one element to the next across a row on the periodic table, each element has one more proton in its nucleus, which means that it hugs its valence electrons more tightly and more intensely towards itself than its predecessor in the row. This takes us to some questions that I'm not going to answer here, but we'll just ask and let you think about. These are in fact thought questions. Why do you think that the first ionization energy is so small for sodium? Why is the second ionization so much larger for sodium? And referring to the periodic table, arrange the following atoms in order of increasing first ionization energy. This table shows us various ionization energies for most of the elements on the periodic table. These are first ionization energies, that is, the amount of energy required to remove a single electron from each of these respective atoms. That takes us to some wonderful questions, beginning with this one. Of the choices below, which one gives the proper order for the first ionization energies? Keep in mind what we're trying to do is sort these elements according to the one that has the highest first ionization energy, then the second highest, third highest, and so forth and so on. Now, I'm not going to do this for you here, but we'll post a link to a separate video in which I do a problem that's similar but not exactly the same as this one that you're welcome to consult if you'd like to for help. Here's another one. You'll notice it's actually the exact same question, just a different set of elements. Once again, you're welcome to click this link for help if you feel that you need it. Here's another one. Which of the following, listed down here, has the lowest first ionization energies of the groups listed? Now remember, the answer is going to be the category of elements that want to give up their first electrons the most. Alright, that takes us to the end of this subject. Let's move on to the next one, which is sizes of atoms, also known as atomic radii. As it turns out, atoms get bigger as you go down a column or a group on the periodic table. Why? Well, because atoms, as you go down a column on the periodic table, have more and more orbitals and more electrons. Hence, they get larger and larger. For example, neon's outermost orbital is a 2p, while argon's, which is just below it, is a 3p. Krypton's, which is below argon, is a 4p. Because the principal quantum number n is changing, going from 2 to 3 to 4, it means the orbital sizes are getting bigger. 4p orbitals are larger than 3p's, which are larger than 2p's, and so forth. So as you go down a column, element sizes get bigger. Now, this is kind of not as intuitive, but atoms actually get smaller as you go left to right across a row or a period. As you think about this, you might wonder why. Because as you go across a row from left to right on the periodic table, you're getting more electrons added to each element. For example, oxygen has one more electron than nitrogen, which has one more electron than carbon, and so forth. So you might be tempted to think, well, oxygen should be bigger than nitrogen, and nitrogen should be bigger than carbon because you're getting more electrons. So as it turns out, it's the exact opposite. Oxygen's smaller than nitrogen, which is smaller than carbon, which is smaller than boron. So why is that? Well, the reason is because as I go left to right across a row on the periodic table, elements also have more protons in the nucleus. Furthermore, elements don't get more orbitals going across a row as they do when you go down a column. They do get another electron as I go from one box to the next going left to right, but one electron doesn't actually increase the size of the element. Having more orbitals does. But as I go from left to right across the periodic table, each element has one more proton than the element that preceded it. That proton in the nucleus attract and suck in the electrons more tightly, which draws them further and further in toward the nucleus, and thereby makes the atom smaller. We can see that exhibited in this table, which shows the individual atomic radii of most of the elements on the periodic table. You can see, with some exceptions here and there, there's a general trend as I go left across a row. The elements get smaller and smaller, and once again the reason is because I get more and more protons in the nucleus, which suck those electrons in tighter and tighter and tighter, making the elements smaller. Contrastingly, going down a column on a periodic table, elements get larger, and the reason is because they get higher energy and hence larger orbitals. Orbitals contribute significantly to an element's size. Here's a link to a cute video that shows this clearly. I'll post a link here on our video so that if you want to, you can click on it and go directly to watching that other video. That takes us then to a series of questions, beginning with this one. Atomic radius generally increases as we move where? Now, I'm not going to answer this for you, but we'll let you think about it on your own. Next, the atomic radius of main group elements generally decreases across a row because of what reason? And once again, I'm not going to answer this for you, but you should know the answer based on the material that I just presented. So this brings us to a different topic. What about ions? For example, do you think that a lithium plus ion would be larger or smaller than a lithium ion? And why? And what about a chloride ion when compared to a regular neutral chlorine atom? Why? And next, what about ions going across a row? How would a lithium plus ion, a beryllium 2 plus ion, and a boron 3 plus ion compare in size? And why? And what about ions going down a column? How would a fluoride or a chloride or a bromide compare in size? And why? Now, I'm not going to address these questions right here, but we'll post a link to a separate video that you're welcome to watch that reviews and discusses this in further depth. Hopefully you know the answers to these questions. If not, I'm going to show you a magical picture on the next slide. Here it is. You're welcome to look at this and see if you notice any trends in the sizes of ions. You should notice that, generally speaking, if I take an element and I add electrons to it, it makes it larger. If I take electrons away from an element, it makes it smaller. As I go across a row, of course, elements get smaller because there are more protons in their nuclei to suck those electrons in, at least generally speaking. And as I go down a column on the periodic table, I get larger because I have more orbitals. That takes us to a series of questions then, beginning with this one. The ion with the smallest diameter, or size, is which of these? Now, I'm not going to do this for you, but we'll post a link to a separate video in which I do one that's similar to this that you're welcome to watch for reference. And now this question. Of the following species, which one has the largest radius? Once again, I'm not doing it here, but you're welcome to follow this link to a separate video in which I do a similar one for guidance if you like. All right, that takes us to the end of this video. Please stay tuned to the next one, in which I'll begin by teaching you about bond enthalpy. Until next time, my beloved students, have an enjoyable rest of your day.